Good morning and hello everyone. It is my pleasure to inform you that the first speaker in this morning session is Professor Oğuz Gülseren from Bilkent University. He is also part of TÜBİTAK Research Institute for Fundamental Sciences as a senior researcher. He is going to give a great lecture entitled Material Properties for Quantum Technologies. Oğuz Gülseren received his BC degree from Middle East Technical University and his MC degree and PhD from Bilkent University. His current research interests include properties of nanostructures like graphene, nanotubes, nanowires, novel two-dimensional materials, theory of self-assembly and self-organization by synthesized and perovskite solar cells, atomic scale friction and biomimetic adhesion from first principle calculations. Professor Oğuz Gülseren is the recipient of the TÜBİTAK Science Award. With this, I want to thank Professor Oğuz Gülseren for all he has done for this school and for our institute, and invite him to begin his lecture. Also, Hocam, you're welcome, please.
Thank you, Alikram Hocam. I think my screen is visible and my voice is fine, I guess.
Yeah, it's looks okay. It looks okay. Can you enlarge a bit again? Or this is final size?
Yes, this is the full screen.
Okay.
Okay. Thank you, Alikram Hocam. As Alikram Hocam introduced, I'm Oğuz Gülseren from Bilkent University, and I am also senior researcher at TÜBİTAK Temel Bilimler Araştırma Enstitüsü. But today, I'll give my 2 cents to this school from a different approach. Up to now, you heard a lot from the different applications, from quantum sensing to the precise measurements and so on. But in all these studies has to be based on some material for physical realization. So today what I will try to do first, just motivate, just repeating a couple of examples from the literature. Then I pick 2 specific examples for today. Then tomorrow I'll go to another family of the materials that are used for quantum technology applications. And I'll try to get the material properties from the first principle approaches. So in experimental, you have to realize, you have to understand what is the physical system, how the atom sits around, and so on. So for that purpose, today, after motivating, I'll introduce the density functional theory and calculation based on that. Tomorrow, mostly I will go through the superconductor materials, and I'll try to introduce some machine learning techniques to predict new materials and so on. So on this, actually, you need to get the precise material properties. This is one side. On the other side, you need to maybe predict new materials with novel properties that can be used with a good efficiency on these applications and so on. So as I said, I'll start with a couple of examples. So I borrowed these figures directly from the literature. So the first, this view graph actually summarizes a lot of things directly from this web page with this title. So if you look at the different systems, this is a quite nice summary. So today I'll try to give the examples from the defects on different solids, mostly on diamond and the boron, hexagonal boron nitride, this type of the systems. But this is not only examples. For example, quantum dots based on like silicon, indium antimony, gallium arsenides. These are quite popular for this type of the applications. Again, during the talks, you will hear about the trap atoms, trap ions, so on, so on. In recent years, also the topological materials are quite popular. I believe we will hear more on these materials from Professor Adagideli's talk as well, and so on. So, as I said, I pick two examples from the defect structures, and I'll try to explain why we do need precise description, and based on that, I'll introduce that's the functional theory type of the approaches. Okay. So again, directly from this web page, they motivate these nitrogen vacancy centers in diamond structures. I'll go through from the original papers as well. So first of all, these are the charge centers. It is possible to manipulate the charge, and I'll show the picture in a minute. It is formed from a nitrogen substitution and nearby vacancy. So these form a pair, and it is possible to manipulate the charge states. And actually, this is quite stable system and has started as a solid state spin qubit with some astonishing properties. So it's magnetically active. And actually, I'll show the energy diagram in a minute. You will see that the ground level triplet state is sensitive to the external fields. It is possible to manipulate this. It is possible a coherent control of the transition on these ground state spin states. So actually, we have the triplet state and the single states, and basically the emission is between through the excited state and the ground state of this spin triplet. In order to, you already see on Professor Onbaşı'nın talk, you need to read out, so you have to manipulate the system, then you have to get the signals out of the system. So you need a great fluorescence properties as well. So on this system, actually, there's a notable photostability on this ground level spin states. So the temperature is one important parameter. So usually the experiments, the prototype experiments observed as the low temperatures, but at the end of the day, you want to extend these applications through the room temperature, high temperatures, and so on. So actually in this MV centers in diamond, that's quite promising for temperature stability as well, and so on. And the quite important property, the single photon emission is very stable with electron spin decoherence time up to microseconds at room temperature and so on. So again, if I continue from the same paper, it's proposed for several applications. As all I have already summarized, long electron spin relaxation time and the coherence time, efficient initialization and optical retard. This is quite proper for the quantum information processing or also sensing activities, sensing applications as well. We already heard on this on previous lectures. But this is the structure of the diamond. In the diamond, probably you might remember, it has a tetrahedral bond, and its crystal structure is the famous diamond structure, just name comes from here. So for example, if you pick one of them, this green ball is one of the carbon atom. Okay, then there are 4 bonds. You are just stretching your arms like this and the legs on the other direction. And the angle between them is approximately 110 degrees. It's a quite strong tetrahedral bond. And it's from bulk properties, we know it has the highest bulk modulus and so on, so on. Here, in order to introduce these single photon emitters, this specific defect centers introduced. Here, what we have, the nitrogen substitution in the place of the 1 carbon atom, then the next side to that is a vacancy. So this is denoted as a ball here, but that's a vacancy actually. Okay, so that forms a nitrogen vacancy center. It's a pair. This is one of the possibilities. So actually you have to create this by ion implantation and so on. There are many other defects, so it is necessary to check stability against these other defects and so on. So that's why actually the high-speed screening without spending so much money on the lab and the experimental effort to screen these through a density functional type of the highly accurate and predictive calculations. So let me continue again. So this is one of the seminal papers published on Proceedings of Nation Academy of Sciences. This is one of the pioneering papers on this area, the quantum computing with defects. Again, this is a summary from this paper. The references you see down there. There are several criteria to use this type of the structure, physical structures for quantum computing as activity. So first of all, okay, I already showed the structure. That structure should result a bound state that is suitable for the qubit operations. Okay, so it must be a paramagnetic long-lived state with the large enough energy splitting between the two levels. So in order to manipulate this, it should be suitable for optical pumping that polarize these qubit states. Then we need a luminescence from, so you have to excite by the photons, then you should be able to get the emission out of from these two states between these two sublevels with enough intensity at the proper wavelength and so on. And this optical transition should not interfere with the electronic states of the host. So here, actually, what I am referring, we have the background diamond structure, we have the electron structure coming from the diamond. then we will have the bound states coming from this MV center, okay? And these bound states should be separated from each other, and this should be stable against the thermal excitation between them. So if you are, I mean, at the prototype, you can show at the low temperature, like the 4 Kelvin and so on, but when you go to the room temperature, there will be a quite appreciable thermal energy, like a 25 millielectron volt. So this stays at least separated by this amount. But this is the states, bound states from this MV center in diamond. Again, still I'm just directly reporting from this literature. You see we have the ground state and the excited states and separated by like almost 2 eV. So you excite this by this incoming photon higher than this energy. You excite the electron from here to that. Then we have this triplet state and the singlet state. And you operate, actually, you manipulate the triplet state on this case. So, so that's the basic bound states you need, but there are obviously several other defects. So this should be screened with respect to the other states and the position on there. So here on this figure energy diagram, you see the valence band and the conduction band shaded by the green and the violet. So that's coming from the diamond structure, okay? That's set by the diamond structure. Then we have the bound states fall within the band gap of the this host material, and you see that the triplet state and the singlet state separated from each other within the band gap of the host. So here 2 examples are shown: diamond and silicon carbide, a specific form of the silicon carbide, and different defects. So here you see the nitrogen vacancy and so on. There might be, in the silicon carbide case especially, you see there are several other states and so you have to be very careful. As I said, they have to be separated and so on. And on the right, what I'm showing, again, for diamond and the silicon carbide, couple of defect centers, okay. Formation energy of these defect centers. So actually, this formation energy is quite high, and so these are the very stable defect centers, nitrogen vacancy centers. This is shown as a function of the Fermi level on this diagram, but you can think you can with this diagram this way. Eventually, these are the charge states. Just playing with the charge state, you can shift the Fermi level. So this diagram, in that sense, is just on the horizontal axis, just following the Fermi level. Actually, you are just following the different charge states and so on. In the silicon carbide case, we have it's more crowded, so there are silicon vacancies, nitrogen and carbon vacancies and so on. But in both of the cases, actually the formation energy is quite high at the order of the several electron volts. that leads to the stable, structurally stable structures as well. Since you want to operate over the long-lived structures without affecting from temperature effects and so on. So the time is fly by, so I want to go a little bit faster. The third example I will give again from the literature. This is from this paper. This is some quite recent paper from last year. This is the paper detailed quite nice review about the hexagonal boron nitride as a single photon source. So here I'm just summarizing. This is a well-known thing, but I'm just summarizing the basic process. Even in the previous example, we already see that we have a two-level, two-level ground state. Okay, so you have the ground state occupied by the electron, then you excite that electron, just absorbing an incoming photon. Okay, so that separation is important. Then you excite with an energy of the photon higher than this energy separation. You excite the electron, that's shown here. Then later on, you have a spontaneous emission. That electron, when it falls back from this excited state, higher energy state, to the ground state, it emits back this photon. And here, in the next slide, I believe I will show, this is quite important to have this emission. And if we can have this as a single photon emitter, then we can use on different application based on this optical process for quantum application, quantum technology applications. Again, this is one of the nice figure. It's just introduce and summarize several applications. So on top here, what you see is the hexagonal boron nitride structure. So this is a two-dimensional monolayer of the structure, and you immediately realize this hexagonal two-dimensional lattice, and there are two colors here, boron and the nitrogen atoms on the structure. Then you realize already some defect centers already introduced. So here we have a carbon substitution over the nitrogen place. So here you see a different color. I don't know if the color is visible, but the nitrogen, the gray atom nitrogen, is substituted, replaced by a carbon atom. This is one typical example. Later on, I will show some experiments and the calculations we do on that type of the system. This is a vacancy. Then on here, when you introduce the vacancy, then some dangling bonds introduced. So by dangling bonds, what I meant, you break the, so if you look at this pristine part, this forms a sp2 type of the bonds on the system. So when you break this one of the bonds, actually you left imbalance charge, as you see on the vacancy centers here. Okay, so this can be functionalized. For example, here it's functionalized by the oxygen atoms with the yellow color you see there. So all these structures introduce bound states, bound defect states, as I showed previously on the nitrogen vacancy centers in diamond, and they use on several different applications, like for the free space communication, optical fiber communication, sensing applications, and so on. Sorry. Okay, I have to go a little bit fast. So again, from the same paper, on this table, what's listed, there are several different effects. Okay, and these are the emission wavelength. So either in terms of the wavelength nanometer or in terms of the energy, you can see the numbers. So these numbers, this emission should be suitable for your operation. It should fall usable energy length. It has a long life. It has to have a long lifetime in order to operate, I believe. So, for example, if you look at the lifetimes, in most of the cases, it's quite short. So, for example, these are some different two-dimensional materials. So, in like a molybdenum disulfide, that's very short. In the hexagonal boron nitride, that's quite promising. That gives at the nanosecond level of the lifetime. The emission wavelength is suitable in different systems as well, and so on. The one quite important advantage of the boron nitride system, you can operate up to quite high temperatures. The other systems, these reported numbers at the very low temperatures, usually like a 4 Kelvin helium, liquid helium temperatures, and so on. Okay, so maybe I should use such a transition slide. So, I mean, in order to realize this system, we need this physical material, then we need to know and screen their properties. So what we can do, either you can go to the lab and take a empirical approach, and you can try to catch the suitable material with the suitable defect center on this example and so on, or either you can go and do the computer experiment. If you have a precise, accurate tools that you can use. That's one of the tools very well established is the density functional theory. So I want to quickly summarize. I don't know if the time permits today. I'll try to go fast. Otherwise, I can use some time tomorrow as well from my time. So here, we want to describe the eigenstates of the electrons on this system, but these are the atomistic system. We have the ground state, but from time to time, actually for this optical properties, interaction with the light and so on, we need the excited states as well. So for this type of the processes, we need an accurate description for the excited states. For the structure and that type of the things like the thermodynamics, chemistry, the ground states is enough and so on. But in the state of the art, now we have a very well established methods for the ground state description, and it is expensive, computationally expensive, but proper methods for the excited states description as well. Okay. So it's a atomic scale. So we are trying to describe this system. In that one, we do have the electrons and nuclei, and we have to describe from quantum mechanics. So we need to solve the Schrödinger equation. I symbolically right here, we have the Hamiltonian, then this is the wave function we have to find out or describe, and this is the corresponding eigenstate with that specific thing. So this looks a very simple equation. It's a generic form. So let me show the Hamiltonian here. Okay, so actually it's quite logical, very simple. You can write down this immediately without studying detailed quantum mechanics books and so on. So the first two terms is the kinetic energy. Okay, so this is the del square. So if you know some modern physics or basics of the quantum physics, what we have the position operator and the momentum operator. Okay, so the momentum operator in real space you can write like a derivative operator. So if you start from that point on, this is like the p square over 2m. Okay, so that's why we have a derivative that describes the kinetic energy for the electrons and for the ions, for the nucleus as well. Then the next three terms is simply a Coulomb interaction between the charge particles. We have the electrons, we have the nuclei, the ions, mostly form the core electrons and the protons from the nuclei. So we have three different interactions, as you can see. So this is the lower letter is the electrons, like the I here. Then this capital letter is for the nuclei, the ion itself. So this is the Coulomb interaction between the electron and the nuclei. Then 1 over Rij. So that's the Coulomb interaction between the two different electrons, and the last term ion-ion interaction. Okay, it's quite logical. It's the usual like a Coulomb interaction and the kinetic energy. That's the exact time-independent, non-relativistic Schrödinger equation. That's enough for us to describe these guys. But the difficulty here, so this is the Schrödinger equation. Again, I am repeating here. So this is the kinetic energy term. This is the potential term just coming from these terms. So this is the complete description, but that's impossible to solve except from the very simple system. So analytically, we can solve just for the hydrogen atom. Then we can introduce like a variation approach. Then we can look at the helium atom or the H2 molecule. But that's it for the analytical approaches. Then you can try the simple numerical approach to solve the atoms, the isolated atoms from the periodic table. Actually, this is tabulated quite nicely, but when you go to the condensed system, a system like that, that's impossible to solve. Since this is a many-body problem, so as I said, we can solve for the two particles analytically, with the numerically. Again, we are restricted like isolated atoms, the small systems, and so on. But in a like a MV center in diamond, just to give an idea, just think the Avogadro numbers, just from the simple chemistry, like 10 to the 23, just the order. So that means at least you have a number of the electrons and the ions at that order. So that means even on this simple Schrödinger equation, you have that many particles. So electrons and the ions, each of them are contributing to this. Then we have spin degrees of freedom as well. And if you think like a three-dimensional space, then you multiply that with the 3. That's an infinitely large dimensional problem, differential equation that we need to solve. That's impossible. So even just think, with the hydrogen atom, we have just a single electron. We can isolate the proton and the electron. We have for single electron, it's a three-dimensional equation. Then we can separate and so on. For hydrogen molecule, H2, then we will have 2 electrons. Then we have to solve this equation in 6 dimensions. Okay, you see, even just with the 2 atoms, that's already becomes 6 dimension without spin degrees of freedom. Okay, so we need something to introduce here. Actually, the first thing is the well-known adiabatic approximation. So our system is something like that. So here, these small green dots are the electrons. They are moving around. Then these large orange balls are the ions. They are moving around as well. But just compare their masses. Okay, a simple comparison. The ions, the nuclei plus the core electrons, are much heavier compared to the single electron. It's approximately like 1,800 times heavier, the ion, compared to the electron. Okay, so that's 3 orders of magnitude difference. So that's that heavy. So that means these tiny little electrons are moving around very fast compared to these guys. Okay, so we are looking at the dynamics of this. Then first, we can separate these two. We can froze the ions. Then we can look at the electrons in the effective field formed by these ions. Like this. We froze this, we get the effective field of the, these ions. We can separate these two. This is called the Born-Oppenheimer approximation or the adiabatic approximation, but this is quite reasonable since these are 3 orders of magnitudes higher, so that means the motion is reflected to that. So we can take a snapshot, we can solve the electronic problem, then we can take another snapshot later on, we can solve the electronic problem and iterate that way. So mathematically, we can introduce that separation. So the ions are moving much slower. I can separate this, that's the kinetic energy term. Then we froze the ions. Okay, so just remember this picture, we froze this, we take a snapshot of the ions. Okay, so I can, there is no motion for the ions at that snapshot. Then this interaction between electron to ions and ions itself, I can describe that as an effective potential there. Then remaining is just the kinetic energy of the electron interaction, then the interaction of the electron set by this effective field. So this way we can separate that. Then at least you reduce the degrees of freedom, just avoiding the nuclear motion. So we can solve the electronic problem for the given ionic coordinates. For the ionic, then we can do the dynamics, classical or whatever it is. Anyway. Okay, so still we get the, this ground state. Let's concentrate on the ground state, but still this is a difficult problem. Still it's a many body problem. Still we have like 10 to the 23 electrons in the system. Still we need further. So historically, I mean, this problem tackled from different approaches, quantum chemistry approaches like Hartree, Hartree-Fock, configuration space, Monte Carlo, and so on. Today, I'll talk about the density functional theory, since this is very efficient and general, and it has very accurate and has predictive power, and so on. So I'll try to summarize, at least give the idea in the last, maybe I can use 10-15 minutes more. Okay, we start 10 minutes late. Okay, so let me go quickly through this. It's mostly developed by Walter Kohn, and Walter Kohn ended up with the Nobel Prize in Chemistry in 1998. So he's a physicist, actually a very genius physicist. But this method is also used in chemistry as well, a lot, in material science, chemistry, physics, and he ended up a Nobel Prize in chemistry. Okay, so the game is this. We have this Schrödinger equation, but this is complicated many-body problem, so can we introduce an effective way to describing this equation? Yes, indeed, this is done with a Consham equation. Okay, I will not go to detail of this, but let me go tell the logic behind that. What we have the wave function, and this wave function depends on the coordinates of each of the particles, electrons in the system. But if we can map or transform the problem instead of a wave function based approach to a particle density approach. So with this density, it will have just 3-dimensional space. It will depend on just 3 coordinates, maybe with the spin. That's it. But here it's a many-body. It depends on each of the electrons. But the combination of this is the density, and it is just an ordinary problem. So if we transform the problem in terms of the density in a non-interacting electrons in an effective potential, then it will be very easy to solve for this in terms of the density. So this original problem, first we freeze the ions, but still we have the this many electrons. So with this mapping, we introduce non-interacting electrons. So this many-body electron problem is just mapped to a single electron problem in terms of the distance that we can solve. Still, we will solve computationally, but that we can solve that problem on this effective potential. Okay, simply like this. So this is called the energy functional. So you see, this is the energy written in terms of the density, electron density in this case. But what we have this external potential, but that depends on the nuclear positions that's already fixed. Then that's integrated by this density. Then we have a functional, a universal functional that gives the total energy of the system. So on this approach, on this Hohenberg-Konk theorem, I will not go to that detail, but it says this functional, it's a functional because it's written, density is a function as well, it's written in that function. It gives the ground state energy if you have the correct ground state density. So actually this can be formulated like a variational problem, then after the variation approaches, you end up, I'll just skip. Okay, maybe quickly I can go through. We have the kinetic energy, this usual term. This is the ionic potential coming from the electron-ion interaction. So this is external potential. This is the Coulomb interaction. Then there is one part that we don't know. I'm not going to that detail. That's the exchange correlation. That's all described in terms of the independent particles, single electron, in terms of the single electron density. Then when you write, direction, you get this Consham equation. Instead of many-body Schrödinger equation, we have a single electron equation that we can solve for different structures and get these quite accurate. Okay. Just accelerating a little bit. Okay, I'm just giving the ideas here. Later on, you can send me an email to ask your questions, anything about the details. I can provide references and so on. But let me summarize here this section by this picture. This is the Kohn-Sham, not Kohn-Sham. It's the Walter Kohn, excuse me. He passed away a couple of years ago. We were lucky he visited us 2005. This is just in front of our building. This is myself, our students at that time. And he delivered a lecture. You see, this is the old title of the giving the seminars talks. We have these TBAE, maybe you don't know this type of the things. You have these transparencies projected to the screen instead of PowerPoints. We share some memory with him as well. So, if I summarize this part, so we are trying to get the material properties or design some materials using some accurate description. So it has to be based on the Schrödinger equation. Here we took the density functional theory approach. Okay. Here, let me just give the take-home message. Here, we don't have any empirical input. It's a first principle, or it's called the ab initio. It has the predictive power. So we can design some system, and if we predict something novel, something very important for quantum technology application, or we can go and make a high throughput screening to generate such a material with a specific properties, we can use this type of the calculation with this predictive power. Here I'm just summarizing this. The only input, you generate your system, your crystal structure, let's say with the defect center, with different type of the defects and so on. So you start with atomic numbers, since you have to identify it's a carbon or it's a silicon or it's a nitrogen. Then you start with the, some positions. Then based on this functional, density functional theory, we can use, we can solve Kohn-Sham equation, get the total energy. From that total energy, we can calculate the forces. From that forces, we can get the dynamical matrices, the vibrations, check the stability of the structures or the vibrational properties, then the emission properties. Then the next step, we can go and look at the excited states and look at the light-matter interaction and so on. But I'm just giving the general idea. Then, just in order there was some confusion through the literature. So this is the Kohn-Sham equation again. I'm just repeating. This is the effective equation that we are solving. It looks like very similar to the Schrödinger equation, but it's a single electron equation. Again, we have this ionic potential, Coulomb potential, and the exchange correlation potential. Then we need to solve this Schrödinger-like equation. This can be done with different approaches. So actually, if you determine the wave function, you solve this and you can reach the energy spectrum and so on. Usually these methods, after this, the methods distinguish with what type of the basis you use to solve this equation, like the Gaussian program that the chemists use the Gaussians to expand the wave function here. Just remember the expansion theorem of the wave function from quantum mechanics. We are trying to describe this. This can be like the numerical atomic orbitals. So this is program like the Siesta that you can do very fast large system calculations. In condensed system, we do use the plane waves, since we want to use the Fourier transform as well for this expansion. Then these are called the plane wave methods based on the pseudo potentials and so on. Again, so how we solve? So we guess a general approach. We start from some approximate wave function. This can be completely random, doesn't matter. So based on this wave function, then we need to construct the potential in order to solve this equation. But here, I'm just showing the Konsham equation again. So this is the kinetic energy, but if you look at the potential terms, we already have the density, okay? And that density is written just as the absolute square of the wave function, okay? So we need to start, if we know this, okay, we can write the potential, but if we don't know, then we have to make a consistent iterative approach. So what does that mean? We start some gas, construct the potential, then first density, using this density, you build up the potential, then you solve the Konsham equation, then as the solution, you get the new wave function, okay? Then at this stage, you compare the previous wave function with the old wave function or the energies. If they are same, it is converged. If they are not same, obviously it is not converged. Then you start the potential again with the new wave function, new density, and you iterate that way. If they are same, you reach the ground state solution, then you stop. After that, then you use that wave function and the energy spectrum to calculate the physical properties of this system. Then you can look at the energy spectrum, then the differences between the state. Using the forces, you have to relax the geometry. So for example, when you introduce the vacancy and the nitrogen to the diamond structure, the structure do not stay that way. Just think the vacancy, just single vacancy, then you just break the bonds, then there is the empty space. Then these atoms will move towards this empty space and so on. This structural relaxation will change the charge state of the atoms around that vacancy and so on. So from that forces, you optimize the geometry. Then from that optimized geometry, you calculate the things. Sorry, this took so long time, but let me quickly summarize, giving some examples. So at the beginning, I showed some boron nitride defect structures on the application. So the things might be quite complicated. On that picture, it shows a very large two-dimensional system and the isolated defect. But in the experimental realization, actually you grow this in terms of the flakes. The flakes might have a finite size, then there might be many more defects and so on. So on this one, we did this several years ago, maybe 5-6 years ago, in collaboration with the experiment. First, they try to grow this hexagonal boron nitride. So here you see the electron microscopy images of these guys. You see these are the layered part, and there is end part has a cap of these layers. So from this experimental picture, we create a model should look like this. So there's a cap region and this layered region, stack layered region, the hexagonal boron nitride structures and so on. So here you see this is like almost the length is like 4 nanometers. This part is like 1.5 nanometers and so on. But this is quite large system for the atomistic calculations anyway. So what we did, we take a flake and look at the different defects, different possible defects on this structure. Here you immediately see, so this is the boron nitride. The orange is the boron, green is the nitrogen atoms here. The first one, so this is the flake structure. This is the size of the flake. The first is the anti-side. So you see here the color is orange again. So one nitrogen is replaced by the boron atomic side. So if you look at the side view, it stays planar and so on. But let's look at this guy, the boron vacancy. So when you just take one boron out, okay, you see these atoms, as I tried to say, try to come closer, but this part, this is further away, that's stay further away. And if you look at the from side, you see that part introduces some curvature, and this is sticking out with the dangling bond, and this looks more cap structure, but it doesn't look planar at all. Then again, another simple one now, the nitrogen anti-side. You see we have a green nitrogen atom instead of boron. This still stay planar, but you see the nitrogen is a little kicked out from the planar structure. Then if you look at the nitrogen vacancy, this is not exactly symmetrical part of the boron. This relaxation is quite symmetrical in this case, but still it introduces a local curvature around the vacancy. So this is what I meant. So the structure also change when you go and realize. So you do the ion implementation and you introduce the vacancy. It doesn't stay planar. So you have to consider this to get the electronic structure energy levels, and also for stability. So if you look at the room temperature with the thermal energy, this structure might be affected from that thermal energy as well. Sorry, I'm just have over time a lot, so very quickly I'll try to summarize. Then we compare this with this experimental pictures, and actually this calculation fit quite nicely to this local structures. This is the electron microscopy image from the experiment. We match this, then we summarize with the energetics. So these are some more. So this is two nitrogen pair to boron pair that falls this curvature a lot. You see in the experiments there are different curvatures on the different angles on different parts. So actually we catch all these and identify what type of the defects will give what type of the local structures and so on. Then if you look at the energetics, so the formation energy is just described. Just if you take away the isolated atomic energies from the total energy, we get the formation energy of defects on different conditions. Here, I'm just summarizing. So we get the formation energies. You see, these are like a 0.4 electron volt. So these are quite stable defects in regarding to that. Sorry, here I couldn't include the energy levels, but these defects gives the bound states as well, and so on. But here my message is, actually I have some more examples from the other transition method we calculated, but I have to stop here. My message here we do need these defect structures, and in quantum technology applications, at the beginning I just summarized nitrogen vacancy centers in diamond and some defect centers in the boron nitrides. These are the long, this has the long lifetime, so these are well established. Here I show a method, that's the functional theory-based calculation, gives an approach to get their material properties, since, as you see, when you introduce the defect, the structure, geometric structure might change, so you might end up different bound states and so on. Then you have to screen these without trying an error type of the approach from the experiment. for understanding these systems. This is the first message. The second thing, these guys, this approach has a predictive power since you are solving the Schrödinger equation in an accurate way. So you can design new materials. You can find novel materials. That's what we are trying to do, using different two-dimensional materials that will give suitable spectrum, suitable properties that can be used on this type of the novel quantum technology applications. I need to stop here. So this needs several hours of lecture, but you can send me an email, ask your questions. I will provide the references and so on. But I'm already over time. Sorry about that. Thank you very much for your attention.
Hocam, thank you very much for your very excellent and comprehensive lecture. Can we now take, before closing this part, a few questions? Yes. Özgür Hocam, please.
Thank you, Oğuz Hocam. It was a very nice talk and very informative for me. So my question is that you said there is an adiabatic approximation at the very beginning that depends on the mass ratio of the nuclei and the electron. But I also heard there are new materials where this approximation fails, like strange metals and so on. So do we need a better condition maybe related to electronic speeds? Maybe there are other mechanisms that can slow down the electrons and make this approximation fails. And if this is the case, what we can do beyond, or can we modify DFT to deal with these problems?
Okay, so that adiabatic approximation is important. So think this way. We start from the time-dependent Schrödinger equation. So there is a time dependence there. With the adiabatic approximation, we are separating these two motions. So actually, full dynamics, we have to include the ions, electrons, and everything as well. To overcome this, to get the ab initio dynamics, it is impossible. It is okay. It is very expensive and so on to solve the ions and the electrons at every step. But there are. Let me give one example. So one approach is like might be this instead of solving full problem. So still we can do the if ions has the fast motion as well and so on. If we cannot separate, still we can assume the adiabatic approximation, Born-Upper approximation. We can fix the nuclear positions with that frozen frame. We can solve the electronic problem for several time steps, 100 steps, 1,000 steps. Then we update and return back to the full, and we do the one step again. We move the ions. I mean, still we have to introduce a faster approach. So this may not doing every step, but doing every 1,000 steps still might help to get a little bit cheaper approaches and so on.
I see. And one last question is that we always talk about density function in this Kohn-Sham method, but in quantum technologies, we need quantum correlations between electrons or maybe even with the nuclei. So if I find the ground state with this DFT method, can I say that this ground state has some entanglement or quantum correlation?
Okay. Yeah. Yes and no. Since we are looking at the ground state here, so when we go to the excited state, at the first approximation, we have this full spectrum and excited states, but still at that one. So for example, when we have the light comes and we excite the electron, we have to actually return back to the time dependent density functional theory. So we have to put to this time dependence. part. This is one approach. Then the second approach, actually, we need to go beyond the ground state standard density function, but the sort of like the GW approach. In that one, you introduce the self-interaction term. That's more complicated, more expensive, but state of the art now, we are able to do GW approximation, then solve the Bethe-Salpeter equation to get the, for example, exponent properties as well, and so on. Yes, I mean, as a first approximation, this is the standard ground state theory, but it is possible to go beyond that. I didn't touch here today, but the GW is, for example, already well-established theory now, even in terms of the computational cost.
Also, James, there's a question in chat from.
Yes, I'm just checking. So, the first question from Aiden: if we solve the Schrödinger equation not for the wave function but for its square density in Kohn-Sham DFT approximation, how we come up with the band structure calculation to go optical properties, etc. Okay, the Kohn-Sham equation. Let me show one more time. We are solving here, for example. You see, this is the Kohn-Sham equation. Yes, for example, this one here we have the still the wave function. Okay, that density is written in terms of this wave function, but this is not the full wave function. This is like the Kohn-Sham orbitals. Okay. This is some technical detail, but they are related with each other. Still, we are solving Schrödinger like this equation. Still, we do have these Kohn-Sham orbitals and the band structure just based on that. So everything formulated in terms of density, but still we do have the band structure and so on. So even still, we can go and do the like a calculation for imaginary part of the dielectric function, we get the optical absorption spectra there. But as I already answered to the Özgür Hoca, nowadays we can go beyond this to the GW and the solution of the Bethe-Salpeter equation to describe the optical properties more properly. And the second question, there's another one. Does atomic vacancy affect biocompatibility properties of the 2D materials? Okay, I mean, it depends on the system, but I might expect they might affect because of this. Okay, I mean, you have to check the different systems. As I have already shown, for example, if you have a vacancy, let me try to find one vacancy picture again. This one.